So the heading for this second lesson is predicting redox reactions. We're going to have to get a few slides in. We've got to talk about oxidizing and reducing agents, and then we'll look at the order that we find them in our reduction table. What are these agents? We need to switch our thinking a little bit, not from what happens to zinc, but what does zinc do to the other chemical? So I've got all the half reactions out, kind of everything we'd want to try to understand this. So zinc is getting oxidized. It's losing 2 electrons. Our copper 2+ is gaining them. We got no spectator ion in our half reaction. So I'm going to put in an arrow. This isn't part of an answer, but it's a visual to understand what's going on. Our zinc is losing 2 electrons. So zinc is sending 2 electrons to the copper 2+. That's the electron flow. That's what creates our products. The copper 2+ ends up neutral when it picks up the 2, and the zinc ends up 2+ when it loses the 2. So we're going to think from this different perspective. The zinc, what does it do to the copper? It allows it to get reduced. If the zinc wasn't there, copper couldn't gain any electrons. It provides the electrons for it to react. So this is where we're going to think of zinc, or another way to think of zinc is as the reducing agent. It causes the other chemical to gain electrons. We've already got a couple definitions now to keep straight. What happens to the zinc? It loses electrons oxidized. It's our Leo. It gets oxidized. What does it cause the other species to do? It causes it to get reduced. So we call it a reducing agent. And these two definitions are always opposite to each other, and most students kind of correctly identify them by remembering that opposite part. We're going to kind of say everything opposite about the copper 2+. Okay. It is reduced, but what does it do to the other chemical? Well, we can think of the copper 2+, the fact that it's positive is pulling electrons away from the zinc. If it wasn't for the copper to help pull and receive those electrons, zinc wouldn't be able to get oxidized. So even though zinc 2+ is our GER gaining electrons, it is reduced. It is our oxidizing agent that causes the other thing to get oxidized. I talk about electrons a lot, but I will not clarify after this that it's always valence electrons. It's always the outermost electrons that are being transferred. So if you remember way back to the Bohr model of the atom with these rings of electrons, it's the ones on the outside that are being transferred. And we always have a certain direction to our transfer. So we have our oxidizing agent, which itself gets reduced. The reducing agent itself is our Leo. They're opposite. So what loses electrons is the reducing agent. The electron flow is always from the reducing agent. It gets oxidized to the oxidizing agent, which is what gains them. And often it takes 3-4 days of this unit for all these definitions to sink in and for you to be comfortable with them. So determine the oxidizing agent, the reducing agent for lead elemental reacting with copper ions, and switching to molecules and ions, elemental chlorine with bromide. Now I have that number line up on the board to help guide you in terms of the loss of electrons and the gain of electrons in terms of charge. So I'll summarize the answers to these shortly. So the answer for A, I'm going to get what gained or lost first. So I'm going to, lead would be starting 0 and going to plus. So 0 going up to 2 plus is the loss of electrons. So this is our Leo, but that's not the question. It's the agent. So if that's losing electrons oxidized, that's going to be our reducing agent. So this must be our GER, the copper to the copper 2 plus to the copper metal. So this is going to be our oxidizing agent. The agents have to be reactants. You're never labeling products as causing something. They're the result of something. So then in B, I would put in the charges, and then what gained, what lost, and then you kind of have the opposite agents. So even though B is element, it doesn't change anything. We've got chlorine. Diatomic elements are 0. So our chlorine is going from 0 to -1. It's becoming more negative. So you either have to do this number line in your head or realize it. So it's gaining electrons because it's going down. So that's our GER, gaining electrons reduced. So if it's reduced, it's the opposite agent. That's our oxidizing agent. So if you're doing a test, the other chemical better be the reducing agent. If you work your way through it, it's -1 to 0. We're going up now. So that's the loss of electrons. So we need to be able to identify our OAs and RAs because of how we're going to use them to make predictions. Our tables are really sort of built from OA, RA perspectives. So we're connecting to our reduction table now with our skills, our vocabulary that we still need to practice. So our reduction tables are made by listing the strongest OA at the top, when most wants to take in electrons all the way down to the least reactive oxidizing agent. Oxidizing agents themselves are reduced, gaining electrons. Oxidizing agent gets reduced. Your brain has to connect that. It takes a while to really get comfortable with it. So OA gets reduced, gaining electrons, hence the taking in. So connecting that statement to your data booklet, hopefully this will help. So we have a reduction table. The strongest oxidizing agent is at the very top, the top left. So that's fluorine. As we go down in the reactant side of the table, we're getting weaker and weaker. The weakest oxidizing agent is at the bottom. Lithium ion really doesn't want to gain an electron and become neutral. Very happy to not have that electron. So that is a reduction. It's just the weakest. That should kind of feel a little bit like an acid-base table. Now we see The opposite trend in the other column. Lithium is a horrible oxidizing agent. But if we look at its product, lithium metal, that is the strongest reducing agent. Lithium metal really wants to do the reverse reaction and make lithium ion and spit out an electron. And as we go up in the table, we get worse and worse reducing agents. We get the weakest reducing agent at the very top. So that's fluoride ion. So the most reactive combination we could get would be fluorine gas. That's our strongest OA. If that reacted with lithium metal, our strongest RA, that's the best combination. If you actually made a battery out of those two, you would get the highest voltage on this table. Then we'll talk about the voltages in the next chapter. So it'll be a while before we start looking at electric potentials. We have to learn a lot of electrochem building block skills, and then we'll apply them to cells, voltaic cells and electrolytic cells. Well, this lesson started with predicting reactions. We're finally going to get there. We've got this strength table, and the position of the OA and the RA is going to tell us something. So predicting if redox reactions occur. So this is not greater or less than 50%. This is a yes or no. If the oxidizing agent is above the reducing agent. So that would look like OA up high. You're going down and to the right to the other column to find the RA. That's the order. Table-wise, we find our two chemicals. The reaction will just happen on its own, under standard conditions. If we have the other sequence, we have an oxidizing agent, you have to go up to the right to find the reducing agent. That reaction will not happen ever on its own. It's not slow, it's not less than 50%. It's a does not happen. Water does not flow uphill. You can force it uphill, and we'll learn in the next chapter you can force non-spontaneous reaction to occur. So the position of metals in a redox table have a huge effect on the value of metals and why we might use certain metals. I'm maybe going to change your perspective a little bit on things. I'm going to look up what would happen if you have some gold jewelry. Gold is one of your chemicals, and you get it in contact with acid. You look that up in your table. Will this react? So we're going to flip back to our acid-base table. Got a clean color. H plus ends up being your oxidizing agent. It's in the first column. And it's located mid-range of the OAs. Gold is fairly up high on the RA column. Gold is a horrible reducing agent. The position of our table, if you take the OA and look at the direction you have to go to get the RA, it's up and to the right. So, does gold react with acid? It doesn't. It's non-spontaneous. Why do you buy gold jewelry for a loved one? Because it's a bad RA, because of chemistry, not because it sparkles or it looks good because of its lack of reactivity. You look at the redox table, a lot of the value of metals comes from its position. Gold really valuable. Okay? You may buy a loved one a gold ring. You go down, so you're getting slightly stronger in the RAs, you'll eventually get to silver. So label those on the board. There's gold, really valuable, maybe $1,800 an ounce. Hey, you don't quite have as much money. Maybe you buy somebody a silver ring. You're even more poor, you know, you're at a few bucks a pound now for copper. You're probably going to get a no if you say, will you marry me? And the ring is copper, but I'll leave that up to you. On the other extreme, you're a really bad chemist. Somebody's going to sell you, I don't know, maybe a sodium ring. Like, oh, loved one, here's a sodium ring. Well, guess what? If I find water, sodium is below water. If you give somebody a sodium ring and they even wash their hands, it's going to react and maybe below the finger right off their hand. Very reactive. So the value of money is the lack of reactivity that gives a lot of metals their value, gold being at the very, very top. So maybe someday you'll ask somebody to marry you, or you'll be on the receiving end, they'll give you a gold ring, you'll be like, yeah, you did well, that's the worst reducing agent you could have given me, you must love me.